Good afternoon to everybody. I want to thank you to be here. And let me to introduce you Adrian Perez Bustamante from the School of Mathematics of the Georgia Institute of Technology. And his talk will about Gevrey estimates and domains of analyticity for asymptotic expansions of tori in weakly dissipative systems. So please, we can start.
Oh, thank you very much. Thank you very much for the space. Thanks to organizers. And well, so let's get started. Well, this is basically the outline of the talk. So I will give you some background of the problem, and then I will present some numerical results, then some rigorous results, and finally I will sketch the proof of the rigorous results that we think is interesting. Okay, yeah, so basically this talk is following this program that is basically the research program that I have been following. So we start doing some numerics. With these numerics, we observe interesting phenomena and make conjectures, and then prove some rigorous results related with the things observed by the numerics. Okay, so let me start with the background. Yeah, so let me introduce the dissipative standard map. So the numerics were done using this map, and the rigorous results also apply for this map. So it's good to have it in mind since the beginning. This is well, this is a map from the cylinder to the cylinder, and it's very similar to the classical standard map, but we are adding a factor lambda, which acts as a dissipation if lambda is small, and we have this nonlinearity, which is in this case I would put the sign function, and we have an extra parameter called the drift parameter, and epsilon is the perturbation parameter. So just let me point out that so we're interested in quasi-periodic orbits, like of this map, and so this drift parameter needs to be added because I mean, if you add a dissipation to a Hamiltonian system, you expect that most of the quasi-periodic orbits will disappear once that you add a dissipation. So in order so if you want that the orbit of a given frequency to be preserved, so you need to add this extra parameter that it would contrarrest the action of the dissipation. So I will talk more about this parameter later, but that's why we need some extra parameter here in this dissipative standard map. And this map can be thought as a discrete model of the spin orbit problem that appears in celestial mechanics. So I think Professor Celletti is an expert in these things. And then so this basically describes the motion of an oblate satellite under gravitational influence. And so you can think the dissipative standard map as a discrete model of this spin orbit problem. Okay. And well, so the dissipative standard map satisfies this property. So the pullback of the symplectic form. So in this case, the standard symplectic form in the cylinder is mapped to a multiple of the symplectic form. So in this case, this multiple is the factor of the dissipation. And well, so for maps that satisfy this property are called conformally symplectic systems. So this structure appears in different problems in dynamics. For example, Hamiltonian systems with the friction proportional to the velocity. For example, in finance, so if you have Euler-Lagrange equations of exponentially discounted systems, right? So these operational problems. So this kind of structure appears in different problems, and well, so Calleja, Celletti, and De La Llave have been developing very systematically a KM theory for these conformally symplectic systems. Just let me mention these two papers, which are important for this talk. And so they have they have many more papers recently, but just let me mention these two. In 2013, so they did a KM theory for conformal symplectic systems, this form. So they proved some a posteriori theorems. So these theorems basically tells you that if you have an approximate solution, you have an approximate invariant torus, then you will have an exact invariant torus. So later, using this a posteriori theorem, so they consider this perturbative problem, in which they consider the perturbation, and now the dissipation will depend on the parameter of the perturbation. Like in this form, well, they prove something more general, but for the sake of this talk, so it's enough to consider this kind of dissipations. And then just note that this problem is a singular perturbation because, for example, for epsilon equal to 0, you have a symplectic map, right? So it's going to be lambda equals 1, and then when you do the perturbation, you go to the conformally symplectic regime. And okay, well, and let me talk more about this work in 17. So let me show you some of the results that they obtained. Well, this consider this problem. They consider a Diophantine frequency. Here, I mean this by Diophantine. And a map from the cylinder to the cylinder. And then so it's conformally symplectic, right? With this dissipation depending on the variable of perturbation. So they also assume that there exists a map K0. So just let me tell you what this means. So this A is for analytic. So it's an analytic function from the torus to this cylinder. So more an analytic embedding. So, and then this row tells you something about the domain of analyticity of this torus. But so you can understand this as an analytic parametrization of a torus, right? So parametrization here embedded in the cylinder. And again, so there must be a map, a parameterization of a torus, and a parameter, a drift parameter, because we need this drift parameter so the quasi-periodic orbits of a given frequency are preserved. So if there exists this map and this parameter satisfying this equation, just let me tell you very quickly what this equation means. This equation means that if you apply the map to a point in the torus, then you stay in the torus, right? So the torus is invariant, and the dynamics in the torus is conjugated to a rotation. So basically, if this parameterization satisfies this equation, so you will have an invariant torus, and the dynamics in the torus is a rotation by little omega. Well, and as is usual in KM theory, you need some non-degeneracy conditions that I will omit right now. But well, so they essentially assume this, and then so they prove that there exists a formal power series for the invariant torus and for the drift parameter, satisfying this equation up to any order. So this is essentially the Lindstedt series. So they prove that there exists Lindstedt series for the quasi-periodic orbits and the drift parameter, and moreover, they prove that there exists a set in the complex plane. This set you can think this as a set of parameters epsilon, right? And functions from this set to, so here you get a parameter of perturbation, and then you obtain an analytic embedding of the torus, and another function which you get a parameter of perturbation, and you obtain a drift parameter. So these functions as functions of epsilon are analytic in this set in the complex plane, and continues to the boundary, and these functions satisfy this invariant equation exactly, right? So, Just let me, so this T omega means rotation by omega. Sorry, I didn't put it here. And then, so basically they prove that there are exact solutions. So these are K, so the torus are preserved for these values of the parameter of the perturbation. Furthermore, so these Lindstedt expansions that they found are asymptotic to these exact solutions of the equation, where these functions are defined, right? So you have Lindstedt expansions, you have also analytic functions, and then they are asymptotic in these domains. And just let me talk a little bit about these domains. So this is a picture of the domain G, considering this dissipation with the qubit order. And then, so basically the set G is the white region here, and the black region is the complement of the set G. So basically, these are some cores that pass through the origin, and then you are taking out balls with center in these cores, and the radius of these balls are decreasing exponentially fast as you approach to the origin. Well, essentially, so inside of these balls is where the small divisors are. So that's why these balls were excluded. So this is the main idea of why they obtained these domains. And well, they conjecture that this domain is qualitatively optimal for generic families of conformally symplectic perturbations, right? So, and they actually proved that this is a lower bound of the optimal domain of analyticity, but it was only conjecture that this was optimal, the optimal domain of analyticity. And some things worth to note here is that this domain does not contain any ball center at the origin, nor angular sectors of width larger than pi/3. So basically, this was the conjecture domain. And then, so now I will start to work about the work that I have been doing. First, I will talk about the numerical results. So the goal here was to study numerically this domain of analyticity, because it was only conjecture to be optimal. So we wanted to study numerically, and also to study some properties of the asymptotic expansions. And then to do these numerical works, we use the dissipative standard map that I presented at the beginning. So, well, so basically we want to use these perturbative expansions we wanted to use the perturbative expansions to study the domains of analyticity. And then, so let me first tell you how can you compute quasi-periodic orbits for the dissipative standard map. So since the dissipative standard map is a map in the cylinder, right? So you can reduce this to one dimension essentially. Like so basically, to find quasi-periodic orbits is equivalent to find a periodic function from the circle to the reals, satisfying, well, a periodic function and a constant and a drift parameter. So here it's always, there is a pair. So you always find a function and just a parameter. So you can find quasi-periodic orbits. And then, so finding quasi-periodic orbits is equivalent to find this function and this parameter satisfying this equation, with this E is an operator defined here. And then this is the expression of the operator. It depends on the terms of the dissipative standard map. And if you are able to find this mu and this u satisfying this equation, then a parameterization of a torus satisfying this equation can be written like this. So basically, this reduces the problem to one dimension. And finding asymptotic expansions of the torus is equivalent to finding asymptotic expansions of this function u. So, and then is what we did. So we considered asymptotic expansions of the function u and asymptotic expansions of the drift parameter, and we solve these equations up to at all orders, and then this is the equations that you get at each order. Just let me point out. So this L omega is an operator defined here, and then this Sk's are the coefficients of the expansion of the nonlinearity in the dissipative standard map. And we can see that we have this shape in the equations. So the first equation, equations up to order 2 are these ones. And then at order 3, so we start to see something different. And for order larger than 4, we see that the coefficient over k will depend on the previous coefficients. And yeah, just let me point out that this change in the shape of the equations, which is given at 3, is given by the order of the dissipation. So we were using this order of the dissipation, but if you use different order, for example, order alpha, so your equations will change at order alpha, and then your dependence will be in k minus alpha. So yeah, so this depends on the order of the dissipation. And basically so once that you have the Lindstedt series, these perturbative expansions, so we study the domains of convergence of this series by using 2 different methods. We used Padilla approximants. That this has been used before by Berretti and Cercia, Falcolini and De La Llave. So they use this to study these Padilla approximants to study the domain of analyticity of the invariant circles for the standard map. So it's well known that for the standard map, you have the invariant circles are preserved, and the perturbative expansions converge, and then they have radius of convergence, like the radius of convergence is like 0.91, if I remember well, or something around that. And then so they use this method to compute this radius numerically, this radius of convergence for the invariant circles for the standard map, for the classical standard map. And then we also use some Newton method that was implemented by Calleja and Celletti more recently. So to study the singularities of the expansions for this dissipative standard map. And then so let me tell you quickly what is this Padilla approximants, in case probably you are not familiar with this. So this Padilla approximants is basically you have a formal power series, and then a Padilla approximant of order PQ is a rational function which agrees with G to the highest possible order in epsilon. So basically you approximate your formal series by a rational function to highest order possible. And so basically the idea is that you expect that the singularities of the series are approximated by the zeros of the denominator of the rational function. And then so if you have a very high orders here, so you are expecting that these zeros will approximate the singularities. And it was essentially, it was what we did. So we computed the coefficients of the Lindstedt series for this function u that will give us the quasi-periodic orbits. And we computed different pairs of Padilla approximants. And we checked the zeros of the denominator of the Padilla approximant. And we did that for different pairs of Padilla approximants. And then we only kept the zeros that were always there for the different approximants that we used. And then so this is what we found. So these roots, these are the zeros of the denominator that we found. And we can see that it agrees. Well, it agrees with the conjectures, with the conjecture optimal domain of analyticity. And just let me point out that So we need to do this with a very, very high precision, because I mean, I was telling that this was used before to study the domain of convergence for the standard map. But for the standard map, the series will converge. So you expect these coefficients to be well behaved, right? So, but in this case, we don't expect convergence of the Lindstedt series, because we expect the domains to be this. So this makes these Padet approximants very, very unstable. So because these coefficients will grow very fast. So that's why we use a lot of precision, and we still we weren't able to go like very, very, very close to zero, right? So but yeah, so but this is evidence that this conjecture is seems to be right. And well, also we check that these singularities that we found are where we expect them to be, because so one of the things that happened, so I was telling you that inside these balls are the small divisors essentially, and then so the zero divisors exactly are when lambda is in the unit circle. And then what we did is that we mapped the singularities that we found by this map lambda, and these are the singularities that we mapped. And this curve is the unit circle, right? So this doesn't look like the circle, but for the scale, but this is the unit circle. So basically, we saw that when we map the singularities by this map lambda, so these are around the unit circle. So these singularities are where they are expected to be. So this also so this helps to verify that these are in fact singularities. And also some interesting thing that we found is that if you do some zooms here there are some clusters of singularities. For example, this figure above is a sum here. Then you see that it has this star shape. And then this figure below is, I think it's a sum here. And it also has this kind of a similar behavior. So that's, I think it is a very interesting structure that is appearing there. And well, we also, to check that these are in fact the singularities, so we also implemented a Newton method to solving these equations. So I will not go into much details about the Newton method because it will take me some time, but it's very similar to the one implemented by Calleja and Celletti. And then so we did that in order to check that there is no monodromy of these singularities. So it was proven by Calleja, Celletti, and De la Llave that these singularities have trivial monodromy. So basically, we do a Newton method, and we did a continuation around curves around these singularities that we found with the Padet approximants. And we saw that if we go around, so we will return to the same function, right? So to the same solution of this equation. And we also noted that as you approach to these singularities that we found with the Padet approximants, so this Newton method will stop to converge as we approach to this singularity, and it's what you expect, because you don't expect to have quasi-periodic orbits in these points. Yeah, so basically it's how we check that these singularities are in fact singularities. And well, so and basically, so the results that we have basically indicates that that there's evidence that support that this is the optimal domain of analyticity. And if this is the domain of analyticity, what one has is that there is analytic functions in these angular sectors. Well, essentially you have angular sectors, and then you have analytic functions here. And then you have asymptotic expansions to these analytic functions in angular sectors. And then so there are some class of formal expansions that turn out to be asymptotic to analytic functions in angular sectors. And so these are algebraic classes of. So let me tell you what is a algebraic class. So given a formal power series, we say that it belongs to a algebraic class if the coefficients satisfy one of these inequalities. So these two are equivalent. So it's only if they satisfy one. It's enough that they satisfy one. And let me tell you what this means. So for example, using the second inequality, if the coefficient satisfies this, then this series, when you divide by these weights, will converge with positive radius of convergence. So yeah, for example, if sigma equals 0, then you will have an analytic function since the beginning. But if sigma is positive, then in principle the series does not converge. But if you put some weights, you have convergence, so you have some kind of regularity. But you still have some regularity in the coefficients. And then, well, for people who knows complex analysis, so this is called sigma Borel summable. Okay. And then again, so using this second inequality for saying that something is Gevrey. Well, if a series is Gevrey, so it needs to satisfy this inequality. And if you take logarithm and divide by k, so then it means that this quantity will behave like a logarithm of k. And then, well, so since we, by the numerical evidence of the domains of analyticity, we think that the expansions are Gevrey, so, and we computed the coefficients of the Lindstedt series, so we computed these quantities. And we use some analytic norm in a neighborhood of the torus. So, and then we compute these quantities, and we want to see if these behave as logarithms of this form. So basically, we computed these quantities, and then we adjusted. We do numerical fits, like raw numerical fits about so these quantities, and we adjusted functions of this form. And for different values of the norm, so they seem to have the same fit. So it seems that they are behaving like logarithms. So and then so it seems that they are in fact Gevrey, at least numerically. And then so we did this first for this frequency, the golden ratio. And more recently, we have extended the computations to different frequencies. So yeah, and then so you can see from the graph here that this seems like a logarithm growth. And well, one thing that these frequencies have in common is that they have the same Diophantine type. So they have the same Diophantine type, and then you can see that well, it seems that there is logarithm growth. And then we also did numerical fits for these quantities. And again, so yeah, so this seems to be like a logarithm, with this. So this sigma would be the Gevrey exponent, right? So we consider these different frequencies. These are the partial fractions expansion, and then we use a lot of precision, right? So because these are very unstable, and well, we use so these numerical fits were used between 100 and 300 coefficients of the Lindstedt expansion. Well, and then so this has made us to this has led us to make conjectures. So first we made a conjecture about the Gevrey character of the Lindstedt expansion. So at first we only studied the golden ratio, the quasi-periodic orbit with the golden ratio. But more recently we have extended these computations, and then so we are extending the conjectures. So given a Diophantine frequency of this Diophantine type, so where this dBT means this, so this is the exponent of the Diophantine type. So we're conjecturing that they are Gevrey, in fact, and the Gevrey exponent is less than this number. So this number is just the largest one that I have found now. So, and then so I'm just putting this number, but so it gives us some idea of what will be the Gevrey character. And also more recently, we have found new patterns in this for these quantities. So a close inspection of these graphs. So you can see that there is some oscillatory behavior. So if you do some zoom-ins, you see that there's like a periodic behavior here. And so this seems to be a period 3, a behavior of period 3. So, and this period 3 comes from the fact that if you remember, the coefficient of order k depends on the coefficient of order k minus 3. And this will explain this period 3. And but other thing that is worth to note is that it seems that the amplitude of these oscillations is decreasing as you increase k. So it seems that the oscillations here are larger and here are smaller. And then to study this amplitude of the oscillations, we consider some moving averages. So basically, we consider this quantity and we subtracted the average of some neighbor points. And these neighbor points, this captures two periods of the frequency. And then, so we expected to centralize the oscillations, basically using these moving averages. And here I'm seeing, I grab these differences. And so this seems to indicate that the oscillations the amplitude of the oscillations is decreasing as a power of k minus k to the negative 1, right? This is, for example, for the golden ratio. And well, this is for other frequency, for the frequency square root of 3, we did the same, and then so the same rate so appears. Actually, it looks very similar, right? So, but they are not exactly the same. And then so we are well, so we are conjecturing now that actually that there are some extra term in the expansion, which is so these quantities like grow as logarithms, right? But they also have this oscillatory behavior, so which is described by a periodic function, and this amplitude is decreasing as a power of k. So this beta will be very close to 1, but it's just a conjecture, right? And then so here you can see a graph of so this is the quantity, and this is the numerical fit, right? The ones, and then there is a zoom. So basically, this was happening. And then so maybe well, I think this is interesting. So maybe later we can explore more these terms. And just let me summarize the numerical results. So basically, before going to the rigorous results, so we verify these theoretical conjectures about the domains of analyticity. And then with this, we establish new conjectures about the Gevrey character of the Lindstedt series. And more recently, we have found new interesting phenomena, like there is this regular behavior of the oscillations, and then so maybe we have approximate these quantities even much better, right? So okay, well that was the numerical work, and then I will go to the rigorous results. And then let me give you the theorem since the beginning. So basically, so we conjecture the Gevrey character of the asymptotic expansions for the dissipative standard map numerically, and now we are proving that they are in fact Gevrey. So basically what we are proving is that so we consider a family of conformally symplectic maps. This family includes this dissipative standard map. But now we are considering the dissipation is of order 1 minus epsilon to the alpha. The nonlinearity can be a trigonometric polynomial. And yeah, so we're assuming that we have Diophantine frequency, which this is what Diophantine means, and we have quasi for epsilon equal to 0, we have invariant circle, invariant torus, where the rotation is given by omega, right? So, and then so for this, we prove that the quasi-periodic expansion of the Lindstedt expansion of the quasi-periodic orbits, sorry, and the expansions of the drift parameter are Gevrey, belongs to a Gevrey class, and then this, and then so this is so just let me point out that this is the Gevrey exponent, right? And then the Gevrey exponent depends explicitly on the Diophantine type of the frequency and in the order of the dissipation. So these things are appearing in the Gevrey exponent that we're getting rigorously. And just let me do some comparison. Just let me do a comparison between the numerics and the rigorous results. So for this dissipative standard map, if we consider frequencies of this Diophantine type, and if we consider this order of the dissipation, order 3, then the rigorous results give us exponent 2/3. So the numerical results were giving us sharper Gevrey exponents. So it seems that our results are not optimal, but it seems that we are not that far from being optimal. So we're thinking so how this can be improved. But well, this is something. And well, so just let me do a quick sketch of the proof. So I don't want to be too technical, but we think there are some interesting ideas here that maybe can be applied to other problems. So what we did is like we developed a quasi-Newton method for this invariance equation. So this invariance equation gives you the quasi-periodic orbits, and so what does this Newton method do? So basically, this Newton method will start with a finite expansion. So finite expansion of this type, and that will satisfy this invariance equation up to order n. So I am denoting, I define this as the error in the invariance equation, and it will satisfy this up to order n. Okay. Well, so this Newton method will take advantage of the conformally symplectic structure that I was talking at the beginning. And this is, so we basically use the so-called automatic reducibility. This is going to be, so this conformally symplectic structure allows us to construct a change of coordinates that gives some cancellations in the Newton equations. So, and other thing that we do kind of in the Newton method is we truncate some quantities. So I will talk more about this, but essentially what you have is you are starting with analytic functions in epsilon. And then so this, if f is analytic, so this is going to be analytic. So and then this has this error is going to be analytic, and it's going to have an infinite expansion. And then so we are truncating these expansions. I mean, it's not necessary to consider everything. We do some truncations. And then so I would talk about more this Newton step, but basically this Newton step, you start with something with an approximation of order n. And so the corrections of this Newton method, you will correct in higher orders. So we're only correcting in higher orders. And yeah, and this is important because so once that we compute one of these coefficients, so it will remain the same because the next correction will be to higher orders. So once the coefficient, for example, the coefficient of 2 capital N is added to the expansion, then the next correction will not change that coefficient because it's only to higher orders. The same for the drift parameter. And again, so this error for this new correction will be will double the order. Well, let me say a little bit more about this Newton method. So to solve this Newton method, at each step of the Newton method, we will need to use we'll need to solve two types of cohomology equations. So the first one, I call it classic, because this appears in KM theory very often, or equations of this form. And this is very well known. And then it is known that as far as omega is Diophantine, so you will have analytic solutions of this equation. And we also have this equation that we call parametric in this case. And then so the problem with this equation is that the small divisors depends on the parameter of the perturbation, which is epsilon, exactly. So the zero divisors are exactly when lambda is in the unit circle, which is some of the things that I was pointing out before. And yeah, so and then so these zero divisors is so thanks, well, not thanks, well, so these zero divisors are the ones that give rise to these domains that I was talking at the beginning. So, and in these domains that I was talking in the beginning, there are no balls with center at the origin containing in those domains. So to get the Gevrey estimates, we really need to have estimates in balls centered at the origin. So this was a problem, because if we consider all the small divisors, so we won't be able to get these estimates in balls centered at the origin. But we note that if the right-hand side of these equations are trigonometric polynomials, then we can get solutions of this equation, which are analytics in balls with center at the origin. So, well, essentially what happens is that if you have a trigonometric polynomial in this right-hand side, so then you will only have a finite number of small divisors, and then they can be controlled. So that's essentially the idea. And yeah, so the point is that, so if we have trigonometric polynomials in this right-hand side, we can get estimates in balls. And then this is one of the reasons for which we are doing the truncations that I was talking before, because if we do the truncations, this right-hand side will be trigonometric polynomials. And then so we will be able to obtain estimates in balls with center at the origin. Yeah, so, and then so one step of the Newton method can be summarized in an algorithm. So of 18 steps. So I don't want you to understand this, because, but I just want to show you this algorithm that can be implemented even in a computer, right? So you can program, you can do a code of this in this. You can implement this, right? Using a, well, anyway. But just let me also point out that if you start with analytic functions, so all operations here, so these are very simple operations. These are compositions, take derivatives, multiplication, composition, take inverse. So if you start with analytic functions, so you will obtain analytic functions at each step. Again, multiplication, composition, sum, multiplication, right? And then here at step 10, we saw these cohomology equations, these parametric cohomology equations that I told you. And then so since we are doing the truncations, so this right-hand side will be trigonometric polynomials. And then this step 10 will give us analytic functions, and then the other steps are like solve this system of equations. So at the end, everything will be analytic, and so you get analyticity here. So you have a expansion, and then so your correction is truncate some expansion. But yeah, so this is basically what you need to do in the Newton method. And so these objects, need to be understood as functions of two variables. So you have the function, the variable theta, which is the variable of the torus, right? So these are parameterization of the torus. And these, as functions of theta, they are analytic in a complex neighborhood of the torus. And as a functions of epsilon, they will be analytic in balls with center at the origin. And well, so this is customary in KM theory. So at each step of the iteration, you will lose some regularity. In this case, yes, you will lose some regularity. And in this case, since we have two variables, so we will lose regularity in the two variables. And then so this is customary in KM theory, and then essentially, so you will be able to estimate this correction in terms of the error, but in different Banach spaces. So just let me tell you how you lose regularity here, like in the variable theta. In the variable theta, you lose regularity in this form. So you have this row represents the width of the torus. So you have analytic function in a neighborhood of the torus of this width row, and then at step H you lose domain like this, but you always have a positive width of analyticity in the torus. So this is kind of customary in KM theory. And in the variable epsilon, we also will be losing domain of analyticity. And then so we have estimates in volts with this radius. And now this radius is of this order, and you can see that this decreases exponentially fast as you you keep going with the iteration of the Newton step. So basically, this means that the domains in epsilon will shrink towards zero. So basically, this means that this quasi-Newton method will not converge as analytic functions, right? But actually, this is not that bad because we are not expecting analyticity because what we have been discussing. But however, this allows us to construct formal power series and get estimates in both of the coefficients, right? Because once that the coefficients are computed, so they are fixed, and then we are ready to do estimates. So just let me tell you how we obtain the Gevrey estimates. So basically, so this is at the step H, we started with something of this order, and the correction basically doubles you the order of the expansion. And once that we computed these coefficients, so these coefficients will not change because the next correction will be to higher order. So we are ready to do estimates for these coefficients. And then so we're ready to do estimates for coefficients in this range. And as I pointed out, we have estimates in volts of this radius. So this radius is decreasing, but we have estimates in volts. And we use Cauchy estimates, so the classical Cauchy estimates. And we can see that the norms of these coefficients are going to be of order 1 over the radius to the power n. So this is a classical Cauchy estimate, complex analysis. And so by how the radius was chosen and these truncations were chosen, then we get that this R is essentially this, right? This 2hn to the tau over alpha. And this n is in this range, so it's this 2n plus 1, 2h plus 1 times n0. And again, so since we are only dealing with coefficients in this range, this 2hn is essentially n of order n, and this 2hn plus 1 is of order n. And then you will have some constant for the orders, and then so this is the Gevrey character, right? So this is what gives you the Gevrey character, and is what gives you the exponent. Well, and so just let me make some final remarks. So the exponent that we found rigorously, as I was pointed out before, doesn't seem to be optimal because of the numerical results. But we think that it might be improved, like choosing different rates of how the domain, because these rates of how you are losing domain in epsilon. So this is where the Gevrey exponent comes. So we are thinking that maybe choosing these rates differently, it can give us different Gevrey exponents, so maybe we can get sharper results. So yeah, so I was talking about these things that we use at the right-hand side of these cohomology equations needs to be trigonometric polynomials. So, I mean, so this picture of the domain of analyticity, sorry, can we go, oh, sorry. Oh, this picture is basically for generic families of conformally symplectic perturbation. So one might think that in fact for more general kinds of conformally symplectic perturbations, you will have Gevrey, the expansions are Gevrey. So our proof essentially works for a family that includes the dissipative standard map. But if we can get rid of this thing of the trigonometric polynomials on the right-hand side, so this proof will work for a much more general family of conformally symplectic perturbations. And so we'll see if this can be done. And finally, so this method of proof, we think that it might work for to prove Gevrey regularity for expansions of other invariant objects in dynamics. Because so basically what we did is we get a functional equation describing an invariant object, and then so we apply a Newton method over this functional equation with these finite power series expansions, and then to obtain the Gevrey estimates, we use estimates in volts. So I mean, so we're thinking that maybe this can be used to prove Gevrey in its regularity for other different types of invariant objects, because so they can be described by functional equations as well, right? So you can try to do some Newton methods to find approximate solutions. And well, and that's it. So thank you very much.
Thank you very much for this very interesting talk. Are there any questions?
I have one.
Yes, so please go.
Do you hear me? So I was wondering, what is about your Gevrey classification in the limit of the conservative case? I mean, there is an exponent with the inverse of alpha, and the limit case should be for alpha going to infinity, isn't it? So it seems to me that everything is lost, but maybe I am lost. So I would ask to you.
Let me see if I, okay, yeah, so we have, so the Gevrey exponent, yeah, depends on the alpha that is given by the dissipation. And then, so you're asking what happens when alpha goes to infinity?
Exactly. That is the limit of the conservative case, isn't it?
Yeah, so you will go to a conservative case. And then when alpha goes to infinity. Yeah, but I mean, actually, it's kind of, because if alpha goes to infinity, so this exponent will go towards 0.
Yeah.
Right, but and then
so you have the asymptotic limit, okay, but the Gevrey classification in the limit is lost, isn't it?
Yes.
Okay.
Actually, when I think you would expect analyticity when the
yeah.
Yes. Well, I don't know if that answers your question.
No, I would just to understand.
I see.
So that's fine to me.
Okay, that's good.
Well, can I make a question related to this?
Yes.
Oh, okay. I don't know if there is somebody else.
No, I don't think so.
Okay, so then my question is, when you have alpha in your pictures, in the pictures that you showed before, either the conceptual one and the Dissipative approximants,
Okay.
you selected a alpha equal to 3, right?
Yes.
So here, okay, alpha equal to 3, so you have 1 minus epsilon to the alpha. were you are you able to can your method allow to compute with the approximants the poles for higher values of alpha? So I don't say 4 or 5, but maybe 10 or 20. So
yes, I think it can be done, because usually, I mean, this alpha would appear in the when you solve the equations at each order, and then basically, so what would happen is that the behavior of this equation will change at order alpha, and the UK will depend of k minus alpha.
yes, formally, I understand that formally you can do it, but can you compute the approximants if alpha is 10, for example, with the same precision? I guess that the computational task becomes heavier.
Yeah, actually, I am one. I think that it would be possible, because you know, I mean, so these Padilla approximants only depend on the function of the UKs, on the coefficients, and then if you have the coefficients, so you construct these polynomials, and then these polynomials are constructed in base of the coefficients of the series.
Yeah.
So basically, epsilon, so it appears, but it appears like a. So what matters most here is the coefficient. So, well, I don't know. Well, I think it could be done, but I don't know if there will be some problems doing that. I'm not very sure if there could be some problems. But I think it could be done. Like, but yeah, I mean, maybe something that I would try to explore. Yeah, but I think it could be done. But I will need to think more carefully about it. So.
Can I make a comment about this?
Yes, sure.
So I think it would be extremely interesting, because the computations that Adrian just showed, for the case of the power equal to 3, so epsilon cubed, there is a pattern, right? So he showed a conjecture. We have a conjecture saying that the oscillation in the coefficients has a period 3. So if you put a
Yes.
So maybe, yeah, there. That you have, yes, a beautiful picture there about the pattern. This pattern. So maybe Adrian can correct me if I'm wrong, but we think this is related to the fact that we use the power 3, right?
Yes. Actually, I would expect, if we use power 10, I would expect like a larger period here.
Yes.
Yeah. Very nice. Thank you, and congratulations for the work.
Thank you very much.
Are there other questions? So I have one. So could you please go to slide 33?
33. Okay. Yes.
When you compare the two values, the one from the theorem and the value of sigma that you have numerically computed, apparently you believe very much on the second digit of the numerical computation estimation, and apparently also on the third one. Since I think that this should be quite critical computations, I am curious to know something more about this.
Well, yeah, I mean, actually, the numerical computation. So we did the fits. So the fits are like I mean, just let me put where is the tables? Yeah. So basically, we computed this, and then we did these numerical fits. But these are like kind of raw numbers. So we just adjusted so the heavy computations are here computing these quantities, and then we adjusted functions of this form, which actually we don't know very much how to verify the accuracy of these numbers, but but these numbers basically what they give you is like so these functions, the growth of these functions like adjust like kind of very well to logarithm growth. But
the effect of truncation is important.
Excuse me?
The effect that you are truncating to order 350, if I say 350.
Yes. Well, so we truncated here because we consider that the errors, because also computing these coefficients, like the UKs, so we consider that the errors in the computation of these coefficients were admissible up to order 300, more or less. So for higher orders, so the errors start to grow, and then we are not very sure of how reliable are those.
So it is difficult to provide an error about the numerical estimation of sigma. So indeed,
yes,
it's larger.
Yes, because so since you don't expect convergence of the series, so these UKs will grow very fast, and so they become very unstable. So these numerical fits were done between these 100 and 300. That so we do it until 300 because it's where we think that the errors are admissible. So we have a small error in the computation, and then so we think that these are reliable data. Yes. Yeah, I don't know if that answers your question or.
More or less, in the sense that maybe it is very difficult to compare the theorem, which is where the sigma is referred to the asymptotic expansion, and here you are just truncating your expansion.
Well, yes.
So it's maybe you should compare the theoretic. I don't know why, but I think that it of this of sigma. So,
yeah. So
in this moment, I don't see how to improve it, but okay, maybe there will be.
I see. Yes, it's a very good point actually. So yeah.
Okay, so thank you. Are there other questions? If not, I would like to thank again Adrian for this seminar, and also to thank everybody for attending the seminar. And I hope you to see here also for the next seminar of the series. So thank you very much.